Hello everyone, I am Shlomi. Lishai Orelidor and I want to present timing attacks using CSS filters. We reviewed the article Cross-Origin Pixel Stealing Timing Attacks Using CSS Filters by Kocher et al. We'll start with an introduction regarding CSS filters and the HTML graphics rendering process.
Cascading Style Sheets, or CSS, is a declarative styling language that applies styling rules to elements of a web document. CSS filters are among the feature families of CSS that allow users to apply personalized style to arbitrary web content. As of recently, the render process is GPU accelerated to make the process faster and more robust. The filters consist of three types. The first ones are the built-in filters, which are effects that can be directly specified as attribute value pairs in a CSS class, as can be seen in the example code on the left, which generates to a blurry bunny. The second ones are SVG, or Scalable Vector Graphics filters, which are similar and can be applied to SVG content. The third ones are CSS shaders, also known as CSS custom filter effects. They allow developers to write OpenGL shader programs and apply the content through separate text files or directly through HTML tags. The shaders are experimental and need to be enabled by the user. DOM, or Document Object Model, is an interface that treats an HTML document as a tree structure where each node is an object representing a part of the document. All of the DOM elements are stored internally as the nodes of the tree, whose root is the document node. The elements have HTML attributes which are mapped into DOM properties.
DOM content needs to be rendered to be graphically visible to the user. The render process starts with the mapping of DOM elements to render objects. The render objects are mapped to render layers if certain criteria are met. An example of such criterion is if the element has explicit CSS properties such as relative, absolute, or transform. Afterwards, the render layers tree is rendered by WebKit. This illustration visualizes this process. At first, each DOM node is mapped to a render object, and then only the render objects that meet the criteria we discussed in the previous slide are mapped into distinct render layers. So how does WebKit render the render layers tree? It traverses the tree from root to leaves. The objects are rendered so that the farthest one renders first, and then the next layer and the next, until we render the nearest object. This happens similarly to Painter's algorithm. In order to determine the depth of pixels, the entire tree is rendered, which is quite inefficient. This inefficiency is what makes timing attack possible. Only after the render layers have finished providing pixels to a buffer in shared memory can a separate browser process take over rendering. Now we'll talk a little about web timing attacks. Timing attacks work when a system takes different amounts of time to process different inputs. They can be categorized into two families. The first one is direct timing attacks. These attacks can be used to determine Boolean values, which could be whether the user is logged in or not, or content data size, such as the size of a user's shopping cart. They are carried between the attacker's browser against the victim's web server. The second type are cross-site timing attacks. They rely on a user to visit and remain on a malicious page while a cross-site exchange is made. All timing attacks described later are cross-site.
Our threat model is when an attacker operates a malicious domain. The attacker is either providing content that keeps the user in a web page for a while. He needs a significant amount of time to perform the attack, or another window is opened, like a pop-up window, in front of the window that's been attacked. Let's talk about some security topics that related to our work. The first one is security in CSS custom filters. CSS custom filters, or you can call it shaders, have access to the rendering of a web content. So, because this content holds some interesting information, a timing attack on the shaders could result in information leaks, such as visited links. When you click a link and the color of the link changes from blue to gray, there is a CSS filter that applied to this link. And if you perform a timing attack, you could know if the user visited that link. But even if that access of filters to the content of the rendering, a timing attack is still possible. Let's examine this code. This is a code of a CSS filter that asks if the color of a pixel is different than black, do a dummy loop for all values of an integer. So an attacker could perform a timing attack and know whether the pixel is black or not because of this loop that waits a lot of time. So CSS shaders introduce some new security concerns. Next, we have security in browsers and GPU graphics rendering. Specifically, we will talk about the Chromium browser, which have two interesting concepts. The first one is that when a GPU is used to perform a calculation about graphics rendering, the result of the calculation is not directly accessed to the application for the browser. So it makes it harder to measure the timing of the GPU performing the rendering operation, which makes it harder to perform a timing attack. On the other hand, we have in Chromium multiprocess model, which means the browser kernel is isolated from the rendering engine. This makes a more noticeable timing differences. So in that model, timing attacks are easier to execute.
Okay, so thank you, Aurel. And now we're going to discuss a JavaScript method called request animation frame, which allows a web page to provide a callback for the browser. This callback function will be called once an animation frame is available for painting. And this is one type of a callback function you can provide. And we're going to use these functions below to calculate the average frame rate. So initially we have start, which sets time. It stores the current time, and it calls step. Step is a function that increments the number of frames and passes itself to request animation frame. That means that once a frame is rendered, we increment the number of frames. At any point, we can calculate the average frame rate by calling update average frame rate, and then we can derive using the start time and t-frames, the variable that we updated in the step function, we can calculate the average frame rate. This is what we're going to exploit as an attacker. We're willing to determine a user's login state. This type of attack is simple and can reveal a significant amount of insight about the user's online behavior. For example, if a user is logged in for an online store, we can derive maybe its age, maybe its gender, or any additional information we're willing to gather. Normally, a login page has different DOM structure than that of a user's home page. So when a CSS filter is applied to documents with different tree structures, the corresponding frame rates are different. And thus, an attacker could determine whether a user has authentication cookies by exploiting this method. So our attack is going to have 7 steps. The first one is to create a malicious reference page. We're basically going to copy the entire website, or more accurately, the login page of the website we're willing to mimic, and store it locally on the attacker server. Next, we're going to create a dummy page in which we will display the original website inside the attacker's domain. So we're going to place an iframe HTML tag with the original website residing in it, but it's going to be located in our attacker's domain. Third, as we require for cross-origin timing attacks, we need to keep the victim engaged. So next, we could perform, we can apply shaders. So we're going to rapidly reapply shaders to the iframe, causing the front page to re-render without refreshing. That is how we're going to measure how much time it takes for the user to load the login page, and we're going to take many measurements. We collect the data and calculate the average frame rate. And then we're going to use the reference page and see how much time it takes for us to render the login page without being logged in. That is this is how we're going to mitigate the network delay and have a better understanding about the timing differences between different devices. And in the 7th step, we're going to analyze the data gathered. As you can see in the paper, they perform this attack on several websites, and in most cases, the difference is very distinct. It doesn't mean that the login page will take more time or less time, as we can see results go in both ways, but the difference is very clear.
Hello, my name is Lishai, and now I will present to you the main part of this article, which is the actual pixel stealing of a 4Gen iframe, which means if there is a victim, I will see what is presented to him on a certain website on the screen. So like the previous attack, this attack also have 6 steps. The first one is, as I'll dive into, expanding a single pixel. In this attack, we want to steal the screen, so we must firstly scan each pixel alone, because if we just scan all the iframe together at once, we'll just get a lot of noise, because the iframe has a lot of black and white pixel and maybe even colorful ones. So we need to each time scan only one and then to different if it was a black pixel or a white pixel. So there is a code to how to do it, and this is very important to do the scan on one pixel each time. The second stage is to choose which iframe I want to steal from the victim. It's important to say here that not all websites can be stolen, because there is an option that you can do that you are not allowed in this to be a forged iframe, and therefore we cannot even request animation frame on this website. And but not everybody doing that. Like even today, this article was in 2013, but even today, websites like Ynet are not using that. So the attack is still pretty powerful. And then we need to actually start seeing what we start deciding what we want to steal from the user. So we need to traverse the page, and if we want to look at the entire screen that he is looking for very good accuracy, we need like 20 seconds for each pixel to be like above 90% accuracy. So for each pixel in the screen, doing this whole scan is going to take a long, and the user might be exhausted and like close the website. So we need to decide which pixel we want to steal. If it's a certain pixel, or if it's a certain center, or if we want to, maybe in a text there is a method that says that for only reading 4 pixels, we can distinguish between 16 letters. So there are very, very good ways to not take all the picture and still know what the text is, and we don't need to actually steal the whole screen. So how you actually do it? So at first, you need to make the might be colorful picture a black and white one. So in order to do that, you need to do all those 4 filters, because you don't just need to make a colorful picture to be a white and black picture. You need all the RGB values to be, if it's black, 0, 0, 0, and if it's white, 255, 255, and 255, because only like doing grayscale will let you be somewhere in the gray area, which is like 100 RGB. So all those 4 filters will give you that each pixel will become or 0 or 255, which is black or white. And then you need to do the really request animation frame, which Lido has explained before me. But you do the request animation frame on the page, and with that, because the article doesn't explain exactly what in it did the difference, but because the values are different, the calculation of the filters, maybe even those filters, took a little different time on each, on the black and on the white. We can know which pixel it was and to get it. We do the request animation frame for, if we want not very high accuracy, 4 seconds, and we can do it in 20 or 100 seconds. And it's important to remember that we need to do it for a long time, because there is a lot of noise and web, and we need to actually be sure to filter the noise out and to check and to get the true results. That's it. The results are in front of you. You can see this is the original text. This is after we do it black and white. And this is the stolen text that they managed to do. This is the most accurate text, but it's really good. And I wanted to talk a little bit about further research. So a little more articles about it became at the same time. So unfortunately for Chrome and Firefox, they needed to re-implement all the filters that they had with sort of optimization based on the RGB values. Like maybe if the values are 0, I don't want to calculate everything because I know I'll get 0, but they removed all those paths, and now they made sure that all the calculation will be exactly the same regardless the RGB value. But still, this is an ongoing attack. People have managed to steal pixels using a floating points calculation, which even if it's the same calculation, it took a different time if it's floating points or 0. And also some ways looking at the cache, which is very interesting. That's it. I hope you enjoy.